Welcome to the first lecture of this week in EE404. In the last lecture, we have seen the important concept, probably it is the most important concept in nonlinear control. So the most important concept in nonlinear control, which is the concept of equilibrium points. So in this lecture, we are going to continue our investigation of equilibrium points. First, we are going to be looking at linear systems and how their equilibrium points would behave. And then we are going to try to concentrate on time invariant and forced systems. And we are going to look at their equilibrium points, how we can define them and how we can actually find them. So remember, if I have the nonlinear system x star is equal to f of x. So far I have defined equilibrium points only for autonomous systems given in this form. An equilibrium point of the system, it is xe in the state space, and I have the state space which is Rn, and a point in state space xe in Rn is called an equilibrium point of the system if f of xe is completely equal to 0. Okay, so depending on the dimension of the system, f is composed of multiple functions, and this notation means that all of those functions are equal to 0 at the same time. This is not the 0 scalar, it is the 0 vector. Okay, when f has multiple dimensions, if the system order is larger than 1, then f of x equals to 0 means that all of f functions are equal to 0 at the same time. And I told you that, or we have written also as a remark, that if a system is started at the equilibrium point, or if it reaches the equilibrium point somehow at some time, then the system state is going to remain there forever. That is the property, defining property of an equilibrium point. So now we are ready to look at linear systems. So when I have a nonlinear system f, then the equilibrium point is defined like this, but I can definitely choose f as a linear function. Therefore, we are free to choose f as a linear function. That means that I can define equilibrium points for linear systems, linear autonomous systems as well. So that is what we are going to do now in the following examples. In the first example, we are given the following linear autonomous system. 1, 2, 2, 6, I have x. And the question is to find the equilibrium point or points of the system. Remember, equilibrium points are only related to the f function in the state dynamics. So the output equation would not change where equilibrium points are. The concept of equilibrium point is only related to the function f, whatever the output equation is. And now I'm given this system. What does this mean? This means that my system is like this. x1 dot x2 dot is equal to, this is a second order system, and I have x1 plus 2x2 and 2x1 plus 6x2. And this is my nonlinear function, f of x1, x2. Okay, so this is my first function, f1 of x1, x2, and this is my second function. In order to be able to find the equilibrium points of the system, I need to equate both functions to 0 and solve so that both equations are satisfied at the same time. So I have x1 plus 2x2 is equal to 0, and I have 2x1 plus 6x2 equals to 0. Okay? And the first equation gives me x1 equals to minus 2x2. If I substitute that into the second equation, since they have to be satisfied at the same time for the equilibrium point, then I need to have 2 times x1, which is minus 2x2, plus 6x2 equals to 0. Okay? But this gives me just the equation 2x2 equals to 0, meaning that x2 should be equal to 0. Okay? And when I go back and substitute this x2 value to the first equation, I would get x1 equals to 0 as well. Okay? So you see that these two equations can be satisfied at the same time if and only if both x1 and x2 are 0. So this should be the only equilibrium point of this linear system. Okay? So xe equals to 0, 0 is the only equilibrium point of this linear system. Okay? But is this really surprising? So probably it is not. Why is that? Because this system looks like this. X dot is equal to AX. Okay? A linear autonomous system would be looking like this. And you see that here, whatever A is, I can substitute X equals to 0 vector here. Okay? Then the right-hand side would be exactly equal to 0. Okay? So we see that here, for any linear system, X equals to 0, which is the origin, is always an equilibrium point. X equals to 0, the origin is always an equilibrium point of a linear autonomous system, given like this. This is quite nice to know. So really, I don't really have to solve for X values. I know as soon as I see a linear autonomous system, I know where one of its equilibrium points is, and it is at the origin. The question is, are there other equilibrium points of the same linear system or not? Okay? And we are going to try to answer that question here. So here, the A matrix that I gave provided us two linearly independent equations. This first equation cannot be obtained, or the second equation cannot be obtained by using the first equation here. So these two equations, they are linear equations, they are linearly independent. That is why we could solve these equations for a single and unique solution. Okay? And how can I understand if an A matrix would provide us linearly independent equations? The answer is coming from an idea or a concept from linear algebra. So the linear independence of these equations are determined by the determinant of that matrix. Okay? If that matrix has non-zero determinant, then its rows are going to be linearly independent. Similarly, its columns are going to be linearly independent. So if the matrix, such a matrix would provide us linearly independent equations if and only if its determinant is actually non-zero. Determinant non-zero means that that matrix is invertible. So let us write linearly independent equations if and only if is shown in mathematics with double-sided implication, if and only if determinant A is not equal to 0. Okay? And furthermore, this is determinant A is not equal to 0 if and only if A is invertible. Okay? So we see that when this matrix is invertible, I see that the origin of the state space is the only equilibrium point that we get. So can I prove this somehow? So can I prove that for a linear autonomous system in that form, if A is invertible, then origin is going to be the only equilibrium point of that system. Can I prove such a thing? And the answer is actually yes. So here I'm given a specific A, and I have found the equilibrium point, the single unique equilibrium point at the origin. Is this a proof? This is not a proof because this is done for a single matrix. I need to prove such a fact for a general A matrix. Okay? So suppose that I would like to write a theorem, and that theorem tells me that if A is invertible, 0 The origin is the only equilibrium point of this system. Here, I'm not given A. The only thing that I'm given is that A is invertible, or determinant A is not equal to 0, and therefore I need to use only that property. And this proof really is really easy. So suppose that A is invertible. Okay? That means determinant A is not equal to 0. Then I can write the following equation. So how can I find the equilibrium points of such a system? What I need to do is to solve this equation. Ax equals to 0, and the right hand side is a 0 vector in this case. Now I know that A is invertible, so why not multiply both sides from the left by A inverse? So A inverse times x, and I have A inverse times 0. Here, how could I do this? I could do this because I know that A inverse exists, and it is finite. That is what exist mean. So in this case, if A is not invertible, I cannot multiply both sides here with A inverse. All right? So now I know that A inverse times A is the identity matrix. Identity times x. A inverse times 0 is going to be still the 0 vector. And identity times x is going to be x itself, and the right hand side is 0. So we get our result. So if A is invertible, the only solution of the equation Ax equals to 0 needs to be x equals to 0, the origin. Okay? So we see here something very important. For a linear autonomous system, if the A matrix is invertible, if its determinant is not equal to 0, then the origin is the only equilibrium point. So now let us try to write our findings. So the first remark that I can make is that x equals to 0, which means the 0 vector, okay, is always an equilibrium point of a linear autonomous system. Okay? So even when determinant A is equal to 0, even when this matrix is not invertible, x equals to 0 has to be an equilibrium point. Okay? Because this equation is always satisfied at x equals to 0. Now we are asking a kind of reverse situation. When x equals to 0 is the only equilibrium point. And the answer is when the A matrix is invertible. So now let us write this as another remark. If A is invertible, then x equals to 0, which is the 0 vector, is the only equilibrium point of x dot is equal to Ax. Okay? So a linear system, if A is invertible, then it's going to have only a single equilibrium point, and that equilibrium point is going to be at the origin. So now let us try to look at the other case. So in this case, I see that the determinant is 6 minus 4. It is 2. It is non-zero in this case. So A is invertible. Now let me look at another case where A is not invertible this time. So our second example is going to be this. X dot is equal to, I have 1, 2, and 2, 4 x. In this case, this is my linear system, and I have to do the same task. Here, I need to find the equilibrium point or equilibrium points of such a system. Okay? I do the same thing here. I can expand this linear function as x1 plus 2x2 and 2x1 plus 4x2. And then equate both functions here. This is f1, this is f2. Equate both of them to 0. 2x1 plus 4x2 equals to 0. So now you see that the second equation can be obtained from the first equation by multiplying both sides of the first equation by 2. Okay? So the second equation is twice the first equation. So somehow this second equation does not give any information. I can extract x1 equals to minus 2x2 and I can substitute here. Then that would give me minus 4x2 plus 4x2 equals to 0 and 0 equals to 0. Okay? So this second equation is redundant. I really do not need it when I try to calculate the equilibrium points of the system. When the first equation is satisfied, the second equation is always going to be satisfied. Okay? So the only equation that needs to be satisfied for an equilibrium point is this. x1 equals to minus 2x2. As soon as this equation is satisfied, or as long as this equation is satisfied, whatever x1 and x2 would be, the vector x1, x2 would be an equilibrium point. Okay? And I know that I have two unknowns and a single equation. That means that I have infinitely many solutions to this equation. Okay? So I have the condition for the equilibrium point. So where are the equilibrium points of such a system? This is my state space, x1, x2. I know that origin is an equilibrium point. Just substitute x equals to 0. It's going to be an equilibrium point. But there are actually more equilibrium points than the origin here. And I know that this equation would denote a line passing through 0 or passing through the origin, and any point on that line is going to be actually an equilibrium point. For example, suppose take x2 equals to 1. If x2 equals to 1, x1 has to be minus 2. So I have this equilibrium point as well. If x2 is minus 1, then x1 is going to be plus 2. So this is another equilibrium point of this linear autonomous system. And actually you can show here that if I connect these dots via this line, this is the line x1 equals to minus 2x2 line. Okay? Any point on this line is going to be an equilibrium point of this linear system. Okay? So really I do not need these specific points here. So all equilibrium points would be living on this line for this linear system. So I have here minus 2 and plus 2. So I see that in this case the equilibrium points are not only a couple of them. There are infinitely many of them. I would have infinitely many equilibrium points, and actually they are very close to each other. If I take any point here in any epsilon neighborhood of that equilibrium point, I would always find another equilibrium point. This is going to be important, and we are going to define something about this. So what can I say here? So suppose that I have this equation which determines the equilibrium points of this linear system. Suppose that this equation is satisfied for a non-zero x vector. Okay? Suppose that I satisfy this equation for a non-zero x vector. Okay? Suppose that x is not 0. Okay? Then I will look at the new vector y equals to alpha x. Okay? alpha is any constant here, any real number. Then I'm going to substitute this y into this equation. A times y is A times alpha x, and this is, alpha is just a scalar. It can get outside the matrix vector multiplication. So I have alpha ax, but I know that ax equals to 0. Okay? So this is alpha times the 0 vector, so that is going to be 0 vector. So what do we see here? If this equation is satisfied for some non-zero x, if the linear system, if the linear autonomous system has a non-zero equilibrium point, then I can scale that equilibrium point with any constant, and that new point would also be an equilibrium point of the linear autonomous, the same linear autonomous system. Okay? So here we actually see this. If I have an equilibrium point here, it is just a vector given like this. The scaling of this vector with any constant would give me another equilibrium point. Okay, here. Or with negative numbers I can scale it. So there would be equilibrium points here. And here I see that alpha can take infinitely many values. That means that if an equilibrium, if a linear autonomous system, if it has a non-zero equilibrium point, then it would have infinitely many equilibrium points, because I can scale that non-zero equilibrium point with any constant, and the new point would be another equilibrium point. Okay? So this is always actually the case, and this only happens when determinant of A is exactly equal to 0. Now look at, so this is my A matrix, and in this case determinant of A is exactly equal to 0. This actually means that the columns of this matrix are linearly dependent, and that means that I can find non-zero x values which would satisfy this equation, A times x equals to 0. As soon as I find a single non-zero x value, I know that I can have infinitely many non-zero x values that would satisfy the equilibrium point equation here. Okay? So when a system, it might be linear or non-linear, has an equilibrium point on a line like this, okay, or in a region of the state space, we would call such equilibrium lines as equilibrium zones. Okay? So this is an equilibrium region, that line. The points on that line is a region of state space points, and every point on that line is an equilibrium point. That is why we sometimes call such lines or such regions as equilibrium zones. Okay? So here we have seen two things. If the determinant is non-zero, then the linear system has a single equilibrium point at the origin. If determinant is exactly equal to 0, then the linear system has infinitely many equilibrium points. Okay? Let us write this as a remark. Remark. Linear systems, linear autonomous systems, either has a single equilibrium point at the origin, this is the case when determinant A is not equal to 0, or they have infinitely many, they have infinitely many equilibrium points when determinant A is exactly equal to 0. So what would happen, for example, if x dot is equal to 0? This is also a linear system, actually. A linear autonomous system. Why is that? Because this is the system 0, 0, 0, 0 times x. Okay? I assume that the system is a second order system, so I have two state variables. And 0 is nothing but 0 matrix times x. So this is also a linear autonomous system. All right? And where do you think the equilibrium points of such system would be? Look at the determinant. Obviously, the determinant A is equal to 0. So this matrix is not invertible. 0 matrix cannot be invertible. And where are the equilibrium points? I will equate the right-hand side to 0 and find which axis would satisfy such an equation. But I see here, whatever I take the value of x vector, that vector would satisfy this equation. So that means that any vector in R2 would be an equilibrium point of this system. So such a linear autonomous system would have infinitely many equilibrium points again, and the equilibrium points would cover the whole state space. In that case, our equilibrium zone would be just the whole state space. Okay? x1, x2, equilibrium points are everywhere in the whole space. Can I check it? Yes, just take any x, okay? If I start the system at any x, I have the equation x dot equals to 0, okay? That means that the system dynamics, the x trajectory will have 0 velocity at any point. That means that wherever in the state space, wherever in R2 I start this system, the system state would not move anywhere. It is going to remain where I started. Okay? So that means that any point in R2 is an equilibrium point of the system. And here we see again the determinant of A is equal to 0. Okay? So now we are going to we're going to try to classify the equilibrium points depending on whether they are alone in some sense in the state space or not. So here I see that whenever I find an equilibrium point, in its very close neighborhood, there is going to be another equilibrium point. Equilibrium points are everywhere. So in any epsilon neighborhood of an equilibrium point, there exists another equilibrium point of the same system. So in some way, here in this case, the equilibrium points are not alone in any way. So I can always find a sufficiently close equilibrium point next to an equilibrium point. So here I have the similar thing. So when I find an equilibrium point, suppose that I take an epsilon neighborhood or epsilon ball around this equilibrium point, and I check if there exists another equilibrium point of the same system in that epsilon neighborhood. Of course, there is going to be another equilibrium point in that epsilon neighborhood, whatever epsilon is, as long as epsilon is positive. Okay? So here I can also say that here the equilibrium points are not really alone. So in any close neighborhood of an equilibrium point, there will be another equilibrium point. Okay? So then, but what about the case when determinant of A is not equal to 0. In that case, the matrix would be invertible and I would have only a single equilibrium point. So you see that around this equilibrium point, I can actually find an epsilon neighborhood in which this single equilibrium point is the only equilibrium point. And here I can make this epsilon as large as possible. It doesn't matter. But somehow we're going to want to define the concept of aloneness of equilibrium points. And this has a specific name in control or nonlinear control theory. And that is the concept of an isolated equilibrium point. If around an equilibrium point, if I can find an epsilon neighborhood in which there exists no other equilibrium point of the same system, then we are going to name that equilibrium point as an isolated equilibrium point of the system. Okay? So let us define this. So I will erase these first. Definition. An equilibrium point XE is said to be isolated if and only if, so this is the definition of isolatedness, there exists an epsilon neighborhood n of epsilon, which is a subset of the state space Rn, such that so here I have epsilon larger than 0, such that n of epsilon contains no other equilibrium points of the same system. Okay? So here I would give you the definition of an epsilon neighborhood. So an epsilon is mathematically defined as follows. So these are the x vectors in Rn such that the norm of x minus xe is strictly smaller than epsilon. Okay? So what do we mean by this double lines here? This is called a norm, and it gives you the magnitude of a vector. Suppose that I have this x vector as given as x1, x2 going until xn, then norm of x would be just defined as follows: x1 square, x2 square, going until xn square. Okay? You might have seen this in the past. So this is called the norm of x, and actually, if you want to be more specific, this is called the L2 norm of x. And here I can try to show you the following points. I can actually define balls with different radius with this norm concept. Let us look at the region that would satisfy such an inequality. If norm of x is strictly smaller than R, which region in two-dimensional state space this would show us, or this would give us? Clearly, this gives us the radius of the, so this is going to be a circle, or it is going to be a ball around the origin the boundary will not be included because of the strictly smaller sign, and the radius of that ball would be just r. Okay? If I change r with epsilon, then the radius is just going to be epsilon, and such a region would be inside this circle. Okay? Now here, this n of epsilon, this neighborhood, is defined with this notation. X is in Rn, and in this case, not only norm of x is smaller than 0, but we have x minus xc, its norm is equal to 0. Okay? In that case, what type of region this would show me, or this would give me? Suppose that xc is here. This is my equilibrium point. Okay? And how can I show the region that is given to me by, or that is described to me by this inequality? In that case, obviously, if xc equals to 0, you see that this turns into this region with the radius epsilon. So here this xc is behaving like the center of this region. Okay? So I would have here this epsilon ball is going to be a ball around the equilibrium point, and the radius is just going to be epsilon. Okay? So this just shows us, this inequality just shows us a region which is centered at the equilibrium point, and the radius is epsilon, and the boundaries of that ball are not included because of the strictly smaller sign here. If I have less than or equal to here, then the boundary would be included as well. Okay? So this is an epsilon neighborhood, and E of xe. Okay? So what does the definition tell us? We are going to call an equilibrium point xc of a system an isolated equilibrium point if and only if we can find an epsilon neighborhood around that equilibrium point containing no other equilibrium points of the same system. Okay? Let me check such an equilibrium point. There is an equilibrium point of this linear system here, and now I'm looking at the epsilon neighborhoods around this equilibrium point. The task is finding an epsilon neighborhood in which there exists no other equilibrium points than this one in the same neighborhood. If I can find such an epsilon neighborhood around that equilibrium point, I would call that equilibrium point an isolated equilibrium point. Okay? And I can make that epsilon as small as possible as long as it is positive. Okay? Any positive number would do, but it cannot be 0, of course. Okay? So here, around this equilibrium point, the question is, can I find an epsilon neighborhood in which no other equilibrium points exist? Whatever I choose my epsilon value here, however small I make that epsilon, there will always be actually infinitely many equilibrium points in the same epsilon neighborhood, in addition to this single equilibrium point. As a result, a single equilibrium point on this line would always be a non-isolated equilibrium point. It is never isolated. It's never alone in an epsilon neighborhood. So as a result, I see that all of the equilibrium points on such a line would be non-isolated They can never be isolated equilibrium points. What about the first case? When determinant A is not equal to 0, in that case x equals to 0, the origin is the only equilibrium point. So whatever epsilon I choose, I would satisfy this criterion. Okay? So whatever positive epsilon I choose, in that epsilon ball, there would never be another equilibrium point of the same system in that epsilon neighborhood. But this is obvious here because this system has only a single equilibrium point. There can never be other equilibrium points in any region I can look at. Okay? That is why I have, so for such a system, I have a single and isolated equilibrium point. Actually, if I have a single equilibrium point, then it has to be isolated. Okay? But in the other case, I have infinitely many equilibrium points, and all of those equilibrium points would be non-isolated. Okay? They are never alone in an epsilon neighborhood. So what can I say here? I can actually say that linear autonomous systems have either single equilibrium point, single and isolated equilibrium point at the origin, or they have infinitely many non-isolated equilibrium points. Okay? That is the ultimate fact about the equilibrium points of a linear system. Now let us try to write this as a remark. Linear autonomous systems have either a single isolated equilibrium point at the origin. This is the case when determinant A is not equal to 0, or they have infinitely many non-isolated equilibrium points. This is the case when determinant A is equal to 0. Okay? So the last thing that I'm going to say in this remark is this. Multiple isolated equilibrium points are encountered only in nonlinear systems. Okay? What is an example? So remember the pendulum system. For the pendulum, we have found two unique equilibrium points. One at the origin, the other one is at pi 0. Okay? So I have the first equilibrium point here at the origin. So this is first state variable, second state variable. x1 is theta, x2 is theta dot. So these are the unique equilibrium points of the pendulum system. Are these equilibrium points isolated? So I'm going to look at the first equilibrium point at the origin. So if I choose an epsilon ball around this equilibrium point, you see that there exists another equilibrium point of the same system in that epsilon ball. Okay? So what am I going to say? This equilibrium point is not isolated. Am I going to say this? Because I could find an epsilon ball in which there exists another equilibrium point of the same system. The answer is actually going to be no here. I cannot say actually that equilibrium point is non-isolated. Now look at look at the definition of isolatedness. An equilibrium point xc is said to be isolated if and only if there is one epsilon neighborhood. I can find a single epsilon neighborhood in which there exists no equilibrium points. So just trying a single epsilon value would not suffice here, would not be sufficient, okay? Because in order to decide on whether an equilibrium point is isolated or not, I need to check all epsilon balls around that equilibrium point, and in order to be able to decide that an equilibrium point is non-isolated, I need to see all epsilon balls, and I need to see that in every one of them there would be another equilibrium point of the same system. But I can decide that, so seeing only that this epsilon, this large epsilon, does not satisfy the criterion, does not tell me that this equilibrium point is non-isolated. I need to check all epsilon balls, and if in every one of them I can find another equilibrium point, then I can say that that equilibrium point is non-isolated. So here you see that thing, okay? I can check any epsilon ball, however small epsilon is, but however large epsilon is. If I look at all epsilon balls, I would always find another equilibrium point in the same epsilon ball, at least one equilibrium point, one other equilibrium point in the same epsilon ball, okay? So this is in order for me to be able to call an equilibrium point a non-isolated equilibrium point, okay? But in order to be able to call an equilibrium point an isolated equilibrium point, it is sufficient that I find only a single epsilon ball for which that property is satisfied, okay? So here, for this epsilon ball, the property is not satisfied. It doesn't mean anything. I need to check other epsilon balls, and I need to look at if the property is satisfied or not. It is only when the property is not satisfied in any epsilon ball that I can call an equilibrium point a non-isolated equilibrium point. But for me to be able to call an equilibrium point an isolated equilibrium point, it is sufficient that I find only a single epsilon ball for which that property is satisfied. So this epsilon ball does not satisfy the property because there is another equilibrium point of the same system in the same epsilon ball. But what about this epsilon ball? If I make the epsilon smaller, then I see that I could find an epsilon ball around this equilibrium point for which the property is satisfied. So I can call this equilibrium point an isolated equilibrium point of the system. Okay? What about this second one? Of course, if I choose my epsilon very large, the property would not be satisfied. But if I make my epsilon small, I can always find an epsilon ball around that equilibrium point which satisfies the property. Okay? So I see that for the pendulum system, I have two isolated equilibrium points. Both of them are isolated. This type of thing can only be encountered in a nonlinear system. Okay? So if you don't know what the system is, and if you see the equilibrium points of the system only, then you can actually decide if the system is nonlinear or not. If you see such multiple isolated equilibrium points, even if you don't know the function f, you can say that that f has to be nonlinear. Because if it was linear, then I would have infinitely many non-isolated equilibrium points or a single isolated equilibrium point at the origin. Okay? Multiple isolated equilibrium points can only be encountered in nonlinear systems. That is a distinctive property of a nonlinear system. Okay? So now we have seen the equilibrium points for autonomous systems. We have investigated both the linear case and the nonlinear case. Now we are going to be looking at the following case. X dot is equal to f of xu. How we can actually define the equilibrium points of such a system, and then we can investigate their properties. So this is the case of a time invariant nonlinear system, and in the earlier lectures I told you that if I select a constant input for this system, I can convert such a system into the form f1 of x, okay, by defining a new f function here, okay. So that is going to be the way to define equilibrium points for time invariant systems in this form. But we are going to see that the equilibrium points that we define for such a system would be dependent on the constant input that we select. And that is going to be actually also a way to control such systems by changing their equilibrium points using constant inputs. But these are for the next, which means second lecture of this week. Thank you very much for watching. Bye.